Welcome to Visual Algebra Lecture 5.1, G-sets and action graphs. A group action occurs when a group naturally permutes a set of states or configurations. Group actions are one of the most important topics in all of group theory, but it's often just not very well understood by students taking algebra. I've read a ton of posts by people who just don't quite get it and are asking for help. You can easily find these posts too. And here's the thing, if that's you, you've come to the right place. What I'm going to show you in this chapter really is, in my obviously biased opinion, the most intuitive and natural way to think about group actions. Like I do with groups, when it comes to actions, I do things a little differently, but I'll leave you convinced that they're absolutely right. For example, I emphasize the concept of a G-set, which is often completely skipped, but that's a huge mistake. We'll talk about group switchboards, action graphs, and fixed point tables. Many of the visuals and analogies that you'll see here are unique to my book and video series, but hopefully not for long. I really think that everyone is going to get a lot out of this chapter, from the novice student to the Ivy League PhD candidate to the seasoned instructor who is trying to better communicate these ideas to a class with diverse mathematical backgrounds. Also, let me warn you, once you start thinking about things in this new way, you can't go back. But that's a good thing. I'm excited to show you how I think about group actions, and I think you're really going to like it too. So let's get started. Intuitively, a group action occurs when a group G naturally permutes a set S of states. For example, the Rubik's Cube group that we saw in the very first chapter consists of the roughly 4.3 times 10 to the 19 actions, and these permute the same number of configurations of the cube. The dihedral group D4 consists of the 8 symmetries of the square. These symmetries are actions that permute the 8 configurations of the square. Group actions formalize the interplay between the actual group of actions and the sets of objects that they rearrange. There are many other examples of groups that act on sets of objects. We will see examples when the group and the set have different sizes, which is not the case in our earlier examples. The rich theory of group actions can be used to prove many deep results in group theory and in other areas of mathematics as well. We have already seen many group actions without knowing it, such as groups acting on themselves by multiplication or by conjugation, or groups acting on their subgroups by conjugation, or groups acting on cosets by multiplication. We've also seen automorphism groups acting on groups. But we just haven't used this terminology yet or formalized it in this way. The group D4 can be thought of as the 8 symmetries of a square. One of them is pictured here, like we saw in the first chapter. There is a subtle but important distinction to make between the actual 8 symmetries of the square and the 8 configurations. For example, the 8 symmetries, which in chapter 1 we called actions, can be thought of as the following: the identity, a 90-degree rotation, a 180 rotation, 270, or any of the 4 reflections. The 8 configurations, or states of the square, are the following. It's what you get by applying these actions to one of these squares like this. When we were just learning about groups, we made an action graph. We called it a Cayley graph, but we'll define an action graph in this chapter. The vertices, or nodes, corresponded to the states, that is these things. The edges corresponded to generators of the group, and the paths corresponded to actions, group elements. Again, that's what we did in the very first lecture, 1.1 of this course. Here is the action graph of the group D4 acting on these 8 squares. And this is a concept that I threw in the beginning of chapter 1 because I wanted you to be thinking along these lines early. I call this a group switchboard, and this is how I recommend you think about actions. So every group element has a button. When you press the R button, these elements all get rotated by 90 degrees counterclockwise. So this configuration goes to that one, which goes to that one, and so forth. And when you press the F button, everything gets rotated about a vertical axis. So this one gets sent to that one. This one here flips across this axis to get to this one, and so forth. And then the key property is that when you press the R button and then the F button in succession, that's the same thing as pressing the RF button. In terms of paths, that's straightforward. Following the red path and then the blue path is the same as following the red-blue path. In the beginning of this course, we picked a configuration to be the solved state. So I picked one of these things, maybe like this one up here, doesn't matter. And then this gave us a bijection between configurations and actions. So we had these 8 configurations, but this one was the identity. This one corresponded to R squared, R cubed, F, RF, and so forth. And the resulting graph, action graph, was a Cayley graph. In this chapter, we will loosen this condition. So we will see examples of groups acting on sets where there is no longer a bijection between elements and configurations. Let me say that one more time for emphasis. In all examples from the beginning of this course, we had a bijective correspondence between actions and states, and this need not always happen. And this is going to be my running example throughout this chapter. Suppose we have a size 7 set consisting of the following, what I call binary squares. The dihedral group D4 acts on the set S as follows. I'm going to describe it intuitively before formalizing it mathematically. So we have a group switchboard as before, and I'm going to highlight R and F because they are generators of D4. And when I press the R button, every square over here gets rotated by 90 degrees counterclockwise. It's like if we have a square here, pressing the R button rotates it, and pressing the F button is going to flip it about a vertical axis. So starting from this state, we rotate it 90 degrees, and we have to do it 4 times to get it back to where we started. But we only need to rotate this thing twice to get back to where we started. And this one, every time we rotate it, it's back to where it started. The flip, on the other hand, is going to fix 3 of these states, but it's going to swap these 2 and swap these 2. Now, one of the key properties of group actions is the same thing that we saw in chapter 1. That is, if we press the R button and then we press the F button, that's like doing red and then blue. Well, there is an RF button, and that better be the same thing as pressing the RF button. So formally, we will say, we're going to do this on the next slide, that when we press the R button, that's going to be a permutation, and then we press the F button, that's the same thing as pressing the RF button. Does that look familiar? That's a homomorphism. But between what groups? Hang on a minute and I'll get to that. The graph that I've drawn here, I'm going to call an action graph. Some books call it a Schreier graph or a coset graph or a Schreier-coset graph. I think action graph is just simpler. It has some properties of Cayley graphs, but there are some fundamental differences as well. One difference, for example, is that it's disconnected. You're never going to have a disconnected Cayley graph. Another example property is that it's not regular. In a Cayley graph, every node locally looks like every other one. But over here, we have this node where there's an outgoing blue and an outgoing red arrow. But over here, we have an outgoing red and an outgoing blue that loops back to itself. And here we have both of these arrows are loops. That said, there is some structure. We can't just have arbitrary components and edges. We will learn about in the next few lectures what type of components or what type of graphs can arise as these connected components. Now, I say it has some properties of Cayley graphs. The fundamental one is that at every node, we have to have one outgoing edge of each type, though it may loop back. So we have to have one outgoing blue edge and one outgoing red edge. Here we have a red edge and a blue edge. So we have to be able to apply every group element to every set element, but it also has to be ambiguous, or it cannot be ambiguous. We can't ever have two outgoing edges of the same type. Let's say a few words about this group switchboard analogy, because I'm going to continue to refer back to this throughout the chapter. And it's not just a training tool. I use it myself to keep track of various interplays between the group and the set. I think it's really useful, and I've been doing this for a long time. Even sometimes in research, when I think about a group action or read a paper, I think about pressing buttons. So suppose we have a group switchboard for G, like I showed you on the previous page, where every element, little g, has a button. If A is an element in G, then pressing the A button rearranges the objects in S. It's a permutation. Let's call it phi of A. If B is an element in G, then pressing the B button also rearranges the objects in S. That's a permutation, and we'll call it phi of B. The element AB also has a button, and we require that pressing the AB button does the same as pressing the A button followed by the B button. And that makes sense. Like if A is the red path and B is the blue path, then the AB button means do the A path, the red path, and then the blue path. Formally, this means phi of AB equals phi of A times phi of B for all elements A and B in G. So this is a homomorphism, but between which groups? Let perm of S be the group of permutations of S. Thus, if S has size n, then this group of permutations is isomorphic to Sn. Now, when we write Sn, we typically think of that as the permutations of the numbers from 1 up to n. So perm of S is like the permutations of my 7 binary squares. Now, some books call the set X, and they write S sub X for the permutation group on X, but if you call your set S, then S sub S is not very good notation. Here's a formal definition. A group G acts on a set S if there is a homomorphism from G to the group of permutations on S. I say G acts on S, we can use the noun form and say that this map phi is a group action. Now let me explain what this map is. So this map will take an element, let's call it little g, and sends it to permutation phi of G. So think of little g, the domain, as like the sticker that's on that button. And phi of G is the result of pressing the button, how it rearranges things. So again, that's what this map is. It's touching a sticker, pressing it down, and that's the permutation. Here's another definition that many, if not most, algebra books skip, which I think is a mistake. A set S with an action by G is called a G-set. And I'm going to call it a right G-set because just like how there's right Cayley graphs, there will also be left Cayley graphs and left G-sets. We are reading from left to right, so I'm going to call these right G-sets. Here's a big idea, and this is really important. An action, that is a homomorphism from G to the permutations of S, endows the set S with an algebraic structure, just like how a binary operation endows a set G, a group, with an algebraic structure. And action graphs are to G-sets like how Cayley graphs are to groups. Here's an example, the one we just saw. Our group switchboard, and with the action that is defined by pressing the R button rotates things 90 degrees, and pressing the F button flips it, we get this algebraic structure on this set of 7 elements. Now, unlike a group, we don't have a binary operation to be able to multiply this times this or something, but we do have an interplay between the group and the set elements, which really is this switchboard. When I say the switchboard, I mean the buttons with the result of pressing the buttons, and that's the homomorphism. Now, I've highlighted this button green. You know why I've done that? Well, you remember back in chapter 1 when we generated the dihedral groups, and we did this in chapter 2 as well, instead of with a rotation and a reflection, with 2 consecutive reflections. Well, what happens if I use that generating set for this action? Here's the action graph. This is a very different looking graph, but it's the same G-set. It's the same algebraic structure endowed on this set of 7 elements. So again, action graphs are to G-sets like how Cayley graphs are to groups. A different generating set will give a different looking graph, but it's the same algebraic structure. Now, I should say a bit about what I've written here, these groups. These groups are something that in the next lecture I will define as the stabilizer. They describe all paths that start and end at this node. So here, every single group element, there's 8 of them, corresponds to a path, and those things all start and end here. Over here, what are the paths that start and end up here? Well, if you do R, so R squared, RF, or the identity, or R cubed, F, then you start and you end up here, and that's this subgroup. And same thing here. What about over here? Here, if you do the identity or you do F, you start and end up here. But here, if you do the identity, you start and end up here. Or if you do R squared F, you also start and end up here. So those are the loops. And similarly here, if you do T or STS, or the identity, or I guess you could do TSTS, you end up back here. And I'll let you check the rest of them. So this is an important concept. It's called the stabilizer. I just wanted to kind of drop this intuition here early so it's not out of the blue when you see it in the next lecture. I said earlier that most books don't even bother defining a G-set. And I think that's a mistake, because it's important to see how an action is more than just a homomorphism. It's a set with an algebraic structure. And I've asked several research algebraists about G-sets. I've asked them questions about them, and in the same month, I got the same answer. And they looked at me and they said, "What's a G-set?" I said, "Oh, it's just a set endowed with an action." And they said, "Oh yeah, I've heard that before." But then, one of them said, "Why define that? There's really no purpose to define a G-set if you already have an action." But to that I say, well, why define a group if you have the notion of a binary operation and properties? Because I think it's important to compare a G-set to a group. And if you don't have the definition of a G-set, then you miss that comparison and those parallels. And as we will see, a G-set is like a generalization of a group. So groups will arise as special cases. You can think of a group as a G-set where where things are completely unwound as possible. And they're like G-sets that also have binary operations. In our binary square example, pressing the R button and the F button permutes S as follows. Now, some people like to write this edge for a loop, but you don't really have to. But R will fix this. It swaps these two states, and then it cyclically rotates these four states. And then F will fix these three, and then it swaps these two. Observe how these permutations are encoded in the action graph down here. You can see them. And once again, next to each S, I have the subgroup that fixes it. This action is an embedding of D4 into the group of permutations of S, which is isomorphic to S7. And here you can see what the generators are. And you can think of the image of this as being the group that you get by multiplying or generated by these permutations, 2, 3, 4, 5, 6, 7, and 2, 3, 5, 7. It's not immediately clear that this is embedding, but one way you could check that is that you actually get 8 permutations from these two things here. So you can just write them out, and once you have more than 4 of them, you can't have more than 4 because you're starting with a group of order 8. But once you have 5 of them, you know that this map has to be 1-to-1. So here's another picture of that action graph where I've numbered these states according to what they are up here. I included this because in my experience when I didn't have this, I had several people asking for more clarification on this homomorphism. Like why is this mapping into S7? And then once I made this picture, I think they got it right away. It is natural to want to characterize all G-sets for a fixed group. And it suffices to consider all connected components. These are called transitive G-sets. I'll have a whole lecture on this later in this chapter. But here's an example. Here are 3 transitive G-sets that we've seen before. Or alternatively, you can think of this entire thing as a size 7 G-set that has 3 components. So when I say characterize all G-sets, you can make even larger and larger ones. I started with a set of 7 binary squares, but I could have started with a set of over 1 million squares like that. I could have used 0s and 1s and 0s and 2s and A's and B's and things like that. But at some point, it's going to be a whole bunch of connected components that look like this. So we really want to know, given D4, what sort of connected components, what graphs can we get like this that actually describe D4 acting on some set? And of course, that's going to depend on the generating set. So really a better question is not what graphs can we get, but what algebraic structures on these underlying sets can we get? Because that structure does not depend on the set of generators used, as we saw a couple slides ago. Later in this chapter, we will learn that every transitive G-set can be constructed by collapsing a Cayley graph by the cosets of some subgroup. When I say collapsing, I mean like the quotient process. But the difference is, in the quotient process, we collapsed left cosets, and for this, we will collapse right cosets. For example, up here, we can think of the nodes, instead of being abstract or having binary squares on them, as having cosets of some subgroup. So if this is the entire group G, so G is D4, then there's only one coset, and if we multiply D4 times R, that coset, that's a D4R is equal to D4. And also, maybe I should write G instead. G F is equal to G. But if we use N, or N is R squared R, or generated by R squared and RF, which is 1 R squared RF and R cubed F, and we multiply this coset by R, now, R is not in here. So we get the other right coset, and well, I said NF, but it's also equal to NR. So this other right coset consists of RF, R squared F, and what's the other one that I'm missing? R cubed. So it's the 4 elements in D4 that are not in here. So you can think of this as these 4 elements as NR, or as NF, or as N times either of these 2 elements as well. Finally, over here, if H is the subgroup generated by F, which is 1 and F, then HR is R and R cubed F. HR squared is R squared and R squared F. And then H R cubed is R cubed and RF. And you could check that if you take H and you multiply by R, well, you will get HR. If you multiply H by R squared, you get HR squared. If you take HR and you multiply by F, you will get RF, and this is going to be R cubed F times F, which is R cubed. So you get those, and so forth. So again, this abstract G-set you can realize as where the nodes are cosets and the edges are just multiplication. And that is what we had in our running example with binary squares. So we're seeing different ways how G-sets arise. This should remind you of when we saw groups in the beginning of the course, and we had some Cayley graphs labeled with configurations, others that were labeled abstractly, and others that were labeled with group elements. Now, instead of the elements being the only things we can label with, we have cosets of arbitrary subgroups. And the elements are a special case of cosets of the trivial subgroup. So that's one way to think about how G-sets generalize groups and how action graphs generalize Cayley graphs. Though the example of D4 acting on our set of binary squares is my favorite running example of a group action, it's important to see other actions by D4 as well, ones that are actually more mathematically relevant. So D4 can act on itself, that is, the set can also be D4, or the set can be the set of subgroups of D4. And there are several ways to define the result of pressing the G button on our switchboard if we want to use one of these sets. We say that G acts on itself by right multiplication. So if we do that, we actually get a Cayley graph as the action graph. We can say that G acts on itself, that is the set S equals D4, by conjugation. And here's what that action graph looks like. And we can say that D4 acts on its subgroups, its set of subgroups, by conjugation. We can't say by multiplication here, because if we multiply a subgroup, we don't get another subgroup, we get a coset. But I want you to notice several things. First of all, every Cayley graph is the action graph of a particular group action. that is, of a group G acting on itself by multiplication. That's one thing. Another thing is we've seen multiple D4 actions before, or I guess variants of our, we saw in the beginning it permuting a set of 8 squares, and then we saw it acting on a set of 7 binary squares, and then we saw some abstract things as well in cosets. But here we have several connected components or transitive G-sets that we have not seen before. So this one that has a red arrow here and then 2 blue loops, and this one has a blue arrow here and 2 red loops, and also this one here. Have we seen? Never mind, we did see this one. That was in our binary square example. So what do you think? Have we seen all possible transitive G-sets with this, with this generating set? I guess if I fix the generating set, I'm asking, have we seen all possible connected action graphs? Something to think about. I think we're missing at least one. I think maybe just one, but we'll answer that pretty soon. Before I finish this video, there's something I have to point out. It's an important observation to make. As we've defined group actions, pressing the A button followed by the B button should be the same as pressing the AB button. However, sometimes it appears like it's the same as pressing the BA button. This is best seen by an example. Suppose our action is conjugation. So if we start with a subgroup H, we conjugate by A like this, A, H, A inverse, and then we conjugate by B, the result is not conjugating by AB, it's conjugating by BA. So it would seem like phi of A times phi of B equals phi of BA, which is not a homomorphism. However, if we conjugate by A in a different way, we say we right conjugate, that is, when we press the A button, H gets sent to A inverse HA, and then we conjugate by B in that manner, then that really is conjugating by AB. So right conjugating by A and by B is the same as right conjugating by AB. Going forward, I will continue to call AH A inverse the left conjugate of H by A, and A inverse HA the right conjugate of H by A. The easy way to remember this is that the left conjugate by A is we conjugate where A is on the left, and the right conjugate we conjugate where A is on the right. So I call this left conjugation and call this right conjugation. And it seems like left conjugation is not a group action using our definition of an action, which is a homomorphism from G to the permutations of S because of this condition right here. But there's a quick way to fix this. The resolution that we'll get to in more detail in a couple lectures. We discussed equivalence of group actions. We'll see that every left action is equivalent to a right action and vice versa. So I'm not going to do that now, but I want to at least tell you what the resolution is really briefly. So there's buttons for all of these. And as I've drawn it, you're thinking that conjugating by A is what you get by pressing the A button. But what if we define conjugation by A inverse to be right? So in other words, if we define conjugation by something to be the right conjugate. So this is what happens when we not when we press the A button, but when we press the A inverse button. So we are right conjugating by A inverse. Then we do this, we are right conjugating by B inverse. And the idea is that when we do both of these, what we are doing is we are right conjugating. So here we are right conjugating by the inverse of the thing that's on the left. And so now the net effect is conjugating by, I claim, BA inverse, which is A inverse B inverse. So now we really do have conjugating by A inverse, and then by B inverse is conjugating by A inverse B inverse. Okay, so that's a preview. More on this in a couple of lectures. I want to finish this lecture by mentioning that some books actually forego our notation using phi, the homomorphism, and they use a different notation to distinguish left versus right group actions. And this is arguably notationally simpler, but I think that it hides some of the ideas of what an action really is, especially the homomorphism property really tells you about, pressing buttons in the switchboard. But it's worth mentioning. So a left group action just means that when you apply G to H applied to S, that's the same as applying GH to S. And a right group action is when you start with S and then you apply G and then you apply H. That's the same thing as applying GH. So think of this as starting with S, pressing the H button, and the G button is the same as pressing the GH button. And then over here, pressing the G button and the H button is the same as pressing the H button and then the G button. We will usually keep the phi, and we'll write things like phi of G, phi of H, S equals phi of GH, S instead of this, and S dot, or times, phi of G, phi of H is S dot phi of HG. And these dots are optional, but they're nice to include. This is a little bit more cumbersome than this, but I think it's just a little bit easier because it's cleaner to see what's a group element and what's a set element. And it's more apparent to use homomorphism properties like this, whereas up here, homomorphism property basically becomes associativity. Some books actually define group actions this way. So here's how they define a right group action. It is a mapping from an ordered pair of a group element and a set element to a set element. So it takes group element A and a set element S, and it sends it to S dot A. And then the following conditions have to hold. This is like the homomorphism property or the buttons property. S dot AB equals S dot A dot B for all group elements and set elements. And then we also need S dot E, the identity, is equal to S for all set elements. And it's not clear, at least to me anyways, that this condition is not implied by the first one. But I think it's not. That's why it's included. And to me, the fact that we can't really tell whether or not it's what is built in and what we can derive from it is another reason why I like the homomorphism definition better. But I do know that for certain things that we're trying to prove, for certain ways of thinking about things, both of these definitions have their place. They both have their pros and their cons. Up here is a right group action, but a left group action is defined similarly. Theorems for left actions have analogs for right actions, regardless as to which definition you use. You basically just hold up your proof and the statement in the mirror. Each left action has a related right action and vice versa. As I mentioned earlier, we will come back to this in a few lectures. We will use right actions, and this is not the standard. Most books use left actions, and we're going to use right actions because we've been using right actions in Cayley graphs without realizing it, and it's really not great to mix. And I will write S dot phi of G to be the element of S that the permutation phi of G sends S to. In other words, where pressing the G button sends S. A lot of books, a lot of proofs you'll see online, will just write S dot G. I like S dot phi of G. I think it's a little bit more clear. If we have a left action, we'll write it on the left like this. Finally, I mentioned when I defined G-sets, I think I called it a right in parentheses G-set, but we can distinguish left G-sets from right G-sets. But we don't need that in the definition. That's more part of the notation. And just like when we defined a group action in terms of a homomorphism from G to the permutations of S, we didn't write down whether it was a left or right action in that definition. Okay, so that's all I want to say for this lecture. The next lecture is on what I call 5 fundamental features of every group action. These are things like orbits and stabilizers and fixators and the kernel and fixed points. These are things that are really important to understand and characterize whenever we have an action. And there will be some fundamental theorems based on these things. Things like the size of the orbit in terms of the stabilizer and other related things like that. So this is really important, and I think a lot of books do not do it justice. And using our group switchboard and action graph analogy, I think there's a lot of mileage that we can get with it that you just really, an intuition that you just don't get elsewhere. So don't go anywhere. I'll see you soon.